All right. Good afternoon, everyone, and welcome to this ENEFIRST webinar on district heating and deep retrofits of buildings. I'm Margot. I'm from the Buildings Performance Institute Europe, and today I'm joined by two ENEFIRST partners, F-Team and Jean-Sébastien. I might wait a bit until more people join, but I see that people are actually joining now. So very briefly before we get started, I'll go over a few housekeeping items just so you know how to participate in this event. So we've taken a screenshot of the attendee interface. So you should see something that looks like this on the upper right corner of your screen. So you're listening in using your computer speaker system by default. So if you prefer to join by phone, you can also select telephone in the audio panel. You will have the opportunity to submit text questions by typing your questions into the question box. You can send your questions at any time during the presentation. We will collect and address them during the Q&A session later on. Please note that we'll send you the slides along with the recording directly to your inbox tomorrow. So I'll now present the brief agenda. So we'll first have a short introduction to the energy efficiency first principle and to the ENEFIRST project by Jean-Sébastien. And then we'll have F-Team's presentation on district heating and deep retrofit of buildings. So don't hesitate to ask questions again via the chat box, as there will be a Q&A and an open discussion at the end. I will go to the next slide. So just before we dive into the topic, I would like to present because this is actually the first webinar of a series of 3. So the next 2 webinars are on April the 13th and on April 27th. So we will put the registration links in the chat box so you can already register for those events. And yeah, I will now hand over to Jean-Sébastien. Jean-Sébastien, the floor is yours.
Thanks a lot, Margot, and welcome everyone. Thanks for attending this webinar. I will have the pleasure to introduce you to the ENEFIRST project, but quickly before that, maybe a few words about the general topic of the ENEFIRST project, which is the energy efficiency first principle. So what it is. Next slide, please. In the project, we complemented the definition that probably most of you know that is included in the governance regulation of the Energy Union to have something that is a bit more operational for the point of view of research and analysis. So what we identified in this principle is that it's a decision principle that requires the comparison of between demand side resources and supply side resources, and with the let's say the main general idea to prioritize demand side resources whenever they are more cost effective or let's say more relevant. And the other main aspect in this principle is to ensure that this comparison is made on a fair basis, what is called here equal opportunity. Next slide, please. So what does it mean in practice? It means the first point is to consider the energy systems as a whole, so considering both sides all together, the supply side and the demand side, and being as systematic as possible in the review of the possible options when an investment is needed, for example. Next slide, please. And the second part about making a fair comparison is to adopt what we call a societal perspective. What do we mean here is to take into account multiple impacts, so not only the direct energy aspect, but also other connected impacts such as greenhouse gases emissions, else possibly GDP or whatever impacts can be relevant according to the policy objectives, because that's a decision principle that is connected to policy objectives. And this other aspect of the societal perspective is to adopt a long-term perspective time-wise. So not only considering the next years, but up to 2050, which is the, let's say, the general time horizon for the long-term energy and climate policies in Europe. Next slide, please. A way to translate that in concrete questions is the checklist that you have here. That can be a checklist to consider when you want to be sure that you implement energy efficiency first in your daily practices and daily processes, especially for decision making. So the first one is the related to considering the demand side resources. So not only the supply side options, but whenever possible, also considering what demand side resources can be relevant. The second one is related to this aspect of a fair comparison. And the third one is the prioritization aspect whenever relevant. Next slide, please. So now a few words about the project. ENEFIRST, which stands for Making the Energy Efficiency First Principle Operational. Next slide, please. The general objectives of the project are altogether to develop and test policy proposals. That will be let's say the ultimate objective of the project. And to contribute to that, there were several steps. And today, this webinar and the whole webinar series is connected to the objective of quantifying the impacts of implementing energy efficiency first. And we had also a workshop in February that was about the EU scenarios. And this webinar series complement that with a number of modeling case studies, and F-Team will present you the first one today. And another point to have in mind when dealing with ENEFIRST is that it's focused on buildings. So in terms of both buildings energy end use and energy supply. And you will find in the slide that will be available on the website afterwards, the links to other European initiative and project that deals with the Energy Efficiency First project. Next slide, please. So what's the theme of the project? You can see here the partners. In general, the project is structured along two main work streams. One that is about the quantitative assessment and modeling, and that's the one that is presented today with F-Team representing IRIS. And we have another work stream that deals with policy analysis. And you can find the reports on the about that also, and the previous webinars that dealt with this work stream on the website. Next slide, please. So I already mentioned the workshop we had last month, and also looking forward, I encourage you to save the dates of 31st of May and 1st of June. We will be jointly organizing together with the Synergies project that also deals with energy efficiency first principle, a conference on energy efficiency first in Brussels. So we hope to see as many of you as possible in person there, and we hope also, if possible, to allow online participation. So we are trying to make it hybrid, but that would be, of course, preferred to meet you in person in Brussels. Next slide, please. And just before I give the word to F-Team, this is a screenshot of what you can find on the website. And I really encourage you to visit it. You can find the reports, different resources as the examples and implementation maps, and all the proceedings from the previous events we organized. With that, I wish you a very fruitful and interesting webinar with F-Team. And F-Team, the floor is yours.
Thank you, Joseph. Good afternoon also from my side. My name is F-Team Popovsky. I work at IRIS. So it's the German Institute for Resource Efficiency and Energy Strategies. And I've been working at ERIS for the past 3 years. Before that, I also worked at Fraunhofer ISI, also here in Karlsruhe, and been working on several Horizon projects since a few years ago, such as Progress Heat, Hot Maps, Heat Roadmap Europe, etc. So today I would like to just a second just to share my screen. I hope you can see my screen now.
No. We could say just before, but yes, now yeah.
Is it?
Thanks.
Oh, okay. And now it should be in full mode, right?
Yes, it works.
Oh, okay, perfect. So thank you. Today I would like to briefly present our results, modeling results from 5 case studies. And on the agenda we have a few points. I will just say a few words about the case studies and the methodology applied, with the focus mostly on the district heating model. In between, we actually plan to have a Q&A session so that we can gather feedback or explain some points, maybe more into details before we go to the results and discussion and conclusion points at the end. Obviously, at the end of the webinar, we can have another Q&A session as well. So very briefly about the background, our research question was to calculate the expected trade-offs between district heating and different building retrofit strategies, with the goal of achieving the climate targets, so having the same greenhouse gas emission savings, which means that in 2050 we have in the buildings, or commercial and residential buildings, we have CO2-free, so to speak, heat supply. For the methodology, we have applied spatial analysis to estimate the distribution, the district heating distribution costs based on heat density maps, depending on the type of the scenarios that we have calculated, and also we have included the individual heat supply options as well, in order to calculate the total cost of heat supply. For the 5 cities that we have selected, which represent almost all 4 European major climate zones, and the scope is on a meso level, or municipal heat and urban planning activities. So we have chosen the city of Karlsruhe here in Germany, then also Budapest in Hungary, Milan in Italy, Warsaw in Poland, and Helsinki in Finland. So here are just some status quo information about the district heating length and the market share and the district heating density. We can see that it varies between the cities, where Warsaw and Helsinki can be probably placed in one group with relatively high district heating market shares above 80%. Karlsruhe and Budapest have quite a similar district heating market share, whereas Milan has a bit lower and has the lowest market share in all of the study objects. The population density, as you can see, it's also quite different within the cities, as well as the linear heat densities that represent the currently installed and operate district heating systems. Very briefly about the methodology, we've used 3 models, which are there's a softly coupled, so to speak, a soft connection between them to assess the total cost of heat for each of the scenarios. For the building energy demand, we used INVERT, which is an energy system model developed by our colleagues at the TU Wien, which provides the heat density. I hope you can also see my mouse here on the screen, which provide the heat density per scenario or on hectare level to the net heat energy system model, which deals with the district heating networks, and also on the other side it connects with the ENERTY model, which is developed by our colleagues at the Fraunhofer ISI to calculate the individual heat supply mix as well. So with this methodology, we are actually able to evaluate the total cost of heat supply, since on the one hand we have the renovation costs, building refurbishment costs. On the other side, we have the heat network costs, as well as the individual heat supply mix. And we have modeled 3 different scenarios with varying average refurbishment rates throughout the years, starting at what is probably the current level of 1%, and then increasing to 2%, which is the goal of the renovation wave, and even 3% refurbishment rate, which can be observed maybe as an extreme. 3% refurbishment rate of the total gross floor area being renovated annually until the 2050 year. So since we are discussing at this webinar mostly the connection between building refurbishment and district heating networks, I will actually focus a bit more on the net heat model and explain the methodology that the net heat model uses. So the basic principle is that we are stacking different files on top of each other, and by this way we can create a matrix system, mathematically speaking, and calculate the cost, number of buildings, district heating length, etc. So there are, in principle, 4 major input files. The first one is the heat demand and the heat density, which comes from the invert model. The second one is the number of buildings, identified buildings within a hectare level. The third one is the streets. We use the street length to calculate the pipe length as a function of the street length and the number of buildings. And at the end, we use the topography or the imperviousness density, in this case, to calculate the costs. But I will show briefly a few examples about each layer before we go to the result part, since it's quite important to actually understand how we've modeled and how we came up with these results. So based on the heat demand and the heat density provided from the invert model and the hot maps tools that we also can use or have used previously, we are identifying regions with a suitable, so to speak, heat density thresholds. So on the left side now you can see the city of Warsaw in 2017, the heat demand. So if we, for example, say, okay, we are interested as a predefined benchmark value, so to speak, only in regions with 20 gigawatt-hour per square kilometer, then we can see with this red value or reddish on the map, we can see those regions that are within this benchmark value. If we obviously increase this value to 40 or 60 gigawatt hours per square meter annually, we can see that these suitable regions are actually shrinking, so to speak, that we look at the hectare level and we calculate the sum, because hectare level it's quite small in principle, so the decisions are not being made on a hectare level if a certain region is suitable for district heating or not. So for these reasons, we look at each cell and we calculate the sum within a radius of 1 square kilometer. And if the sum is within these predefined threshold values, then we assume that this region, also in the future, with the future heat densities, is suitable for district heating network. Here are some classification or assessment of suitability for the construction of district heating network based on a document provided here by the Energy Agency in Baden-Württemberg in Germany. And in this case, we've used 25 gigawatt hours per square kilometer, which is somewhere between the recommended values for low temperature district heating networks and district heating networks in new buildings. Of course, we have done this decision so that in the future we can actually see which regions are suitable for district heating network. So this was the predefined value. So we also can vary this value, and I will briefly show that in the results as well. In the second step, what we use is we are trying to identify the number of buildings within the cities, and for this purpose we use the OpenStreetMap tool, and we applied several different filters, such as the floor area, type of building, if there's address provided, etc., in order to identify all of the residential and non-residential buildings. And at the second step, we define a correlation between the district heating share and the number of connected buildings. So if we have a look at if we know that in a certain city, or we want to achieve, let's say 50% district heating market share, we can see that to do so, we have to connect at least 30% of the buildings, since not all of the buildings have the same heat demand. And based on the census data for Germany, and we actually have extrapolate also this value for the other cities as well. And the goal it's actually to get the number of buildings for each raster cell. In the second step, we have a look at the street length and the roads. Here is also for Warsaw an example. Why do we actually do that? We use the same methodology that colleagues here in Germany developed, meaning that if I have 30% connection rate in the building, that means that I need to use around 50–55% of the street in order to be able to connect. Obviously, we are making these assumptions because we don't know for each city which building is actually connected currently, and obviously we cannot know if the district heating network is expanding, we cannot know which buildings will be connected to the network in the future as well. Nevertheless, we are doing this. We are applying this methodology to try to estimate the number of connected buildings, and obviously the street and pipeline required to connect all of these buildings. Additionally, we also use an assumption that around for each of the, apart from the street length, we have 10 meters per building to connect it. Then at the third step, we actually have a look at the impervious density. And why we actually do this? Because the impervious density can give us the first and rough estimation about the potential cost. We're doing that because we want to differentiate. As we all know, it's quite different to build any infrastructure in densely populated areas. So the impervious density is actually showing us what is the amount of land which is covered by concrete and asphalt. And if it's above 80%, then we can assume that the highest cost can be applied in these areas. Area 2 is represents areas with a dense urban fabric between 50 and 80%, and area 3 are medium to low urban fabric areas with impervious densities below 50%. And obviously, to differentiate between cultures, we use a different labor cost index in the construction sector, as well as a price level index for machinery and equipment. And the goal is to have the specific construction costs also per raster cell. So on hectare level, 100 meters, 10,000 square meters level, so to speak. Because we use the top-down approach, at least the equation from the top-down approach from our colleagues from the heat roadmap Europe, which you probably have seen and you're probably familiar with it. But in order to, since we want to take all of the local particularities, we have applied also this bottom, some combination between the top-down and bottom-up approach. As you can see, our colleagues have used this ingenious method to actually calculate the capital distribution costs, and we have made a few changes since they are using the plot ratio or the building density to calculate cost coefficients. We are using the imperviousness density. For the pipe length and pipe diameter, we use the length of the streets and the connected buildings, and for the pipe length and for pipe diameter, we use the mass flow and the maximum flow velocity, assuming a constant pressure drop, for example 150 Pascal per meter. And by doing so, we are actually able to calculate a specific investment cost for euro per meter for all of the areas and all of the different pipe diameters. Last but not least, we know that the district heating supply mix has to change. And in order to be able to compare the building refurbishment impacts across cities and scenarios, we have assumed a generic fuel mix in 2050. This generic fuel mix has been applied in all of the case studies. What actually varies only are the installed capacities of the required heat supply plants. Nevertheless, the mix consists of heat pumps in 2050, partially industrial excess heat with 25%, synthetic gases with 15%, or also biomass and biofuels with 15%, followed by geothermal with 10% and solar thermal with 5%. And also, maybe just a summary of the methodology before I try to answer some of the questions that I hope you have. Since I try to put a lot of information in a very short period of time, as a summary, what we have done is, first, we have 3 different building refurbishment scenarios. Second, we have this benchmark value to predefine, so to speak, suitable district heating regions. And a third step, we are varying the connection rate of the buildings. And the fourth step, we are calculating the individual heat supply technologies classified in these 8 building types. And these are the specific costs, so to speak, that we calculate for each of the building type houses. And at the end, we have the total cost of heat for the scenarios, which include the building refurbishment costs, the district heating supply costs, as well as the individual heat supply costs. So with this, I actually I'm finished with the methodology part, and I would like to answer a few questions, which I think it will be quite suitable before we go to the results. So I don't know if you have written something in the chat, or maybe Jean-Sebastian.
Yes, there would be two questions for you to start the discussion. The first one would be what makes the methodology that you have presented different from, let's say, a classical energy planning study or a classical study that a municipality would do to identify the needs and plan the development of district heating?
Well, with a few exceptions where you have a heat planning on a municipal level, obviously there are many cities that are already doing this. But if I have a look at Germany, this is only required now only in one of the German states, so only in Baden-Württemberg. So for many cities, this is actually a completely new method. So they never applied anything similar to this. They have been developing the infrastructure. Well, parts of it's already due to some historical reasons have been developed. Other parts have been developed based on a very brief, so to speak, cost-effective assessment, without explicitly considering the energy efficiency measures within the building sector. And this is something that we are also considering in our analysis. And this is also quite new in Germany, and I assume that it will be also applied on a national level quite soon, where all of the municipalities above a certain threshold will have to conduct such heat planning activities, which are quite similar to something that many, for example, Danish municipalities are already doing. But based on what we have seen, obviously I cannot talk about all European cities, but based on what I have seen in Germany, in many cases, this was not considered at all. But in some cases, it was a legacy infrastructure that was being constantly expanded. In other cases, there was, let's say, some large consumer that have driven the costs, or that have driven the need of the municipality to invest in some infrastructure. And yeah, this should be changed, because anyhow, if we continue doing this, we'll risk in having in 2050 probably largely oversized network, which if we know, if the costs start increasing and people start disconnecting from the network, then it will be also yeah, quite challenging for the municipalities and for the utilities to actually continue yeah, using this infrastructure as well.
And it makes a nice transition to the second question, which would be how easy or how difficult would it be for a municipality, or let's say another local stakeholder, to apply this this methodology based on your own experience now that you have done
actually, it's not that easy. It's a bit more challenging, but we have seen that in the past few years there are many projects, many tools that have been developed and are still in the development phase to assist local stakeholders to be able to conduct such an analysis in a, let's say, a meaningful period of time. Otherwise, obviously, we are aware of the challenge that many utilities have, that are, so to speak, understaffed, and that they cannot deal with some of the issues that has to be dealt currently, and they cannot invest a lot of time in using these tools or this analysis. So it's, I would say, it's a medium on the level of low, high, and medium difficulty. So currently it's at the medium difficulty, but I think that we are progressing in a good direction. So in maybe a few years, there will be also open source tools on the market that will be able to provide meaningful data analysis in a very short and brief period of time. Obviously, this doesn't replace detailed planning on the ground. So this is just to see, okay, to which extent does it make sense to invest in this type of infrastructure, and does it make sense in some cases to invest more in building efficiency than in replacing very high heat generation capacities. So this is something that this type of tools can actually provide the stakeholder with this type of information. But a detailed planning on the local ground, so to speak, if I have to, let's say, is it a 100-meter pipe or 110-meter pipe, which diameter, of course, this type of tools and analysis do not replace these activities.
Okay, so would you say that the main difficulties are in terms of data availability or data access or collection, or
data availability? Of course, it's always an issue. We are using some generic data sets. The better the data, obviously, the better the results. But we know that in many cases the data is not available. Even we've seen that even in the existing network, in some cases, even the utilities, they don't know what is, for example, the pipe diameter, since this was some pipes were installed 50 years ago. So they try to now digitalize all of the plans that they have. So data availability is obviously an issue. but as well as the usability of the tools. So instead of having, let's say, 2 or 3 different tools, combining them to have a meaningful results, it's obviously it should be only probably one tool that can consider all of the questions, but this is somehow challenging, and still I haven't seen one tool that can provide this analysis on such a high resolution spatial level of 1 hectare. So I hope this answer is sufficient. I don't know if there.
One new question from Diana Stanica. Are district heating temperature levels considered in the analysis? And she commented that existing buildings generally require high heating temperatures, whereas new and refurbished buildings have lower temperature demands.
Yes, this is a very good question. We, over the years, obviously the temperatures, they will reduce, since we don't know at what point the city will be able to reduce it, and at what point the buildings, exactly at which year the buildings will be able to use low temperature. We have applied, to be on the safe side, so to speak, we have applied a bit higher temperatures, an average temperature of 90 degrees Celsius, supply temperature, and 60 degrees Celsius return temperature.
Okay, all clear. I think you can now go to the second part of your presentation. Thanks a lot for your answers.
No, thank you very much for the question. So if we have a brief look at the heat demand development, we can actually see that energy demand savings between 16 and 40% can be expected. This value varies between the cities, mostly due to for example, the heated floor area. We see that the models, they consider an expansion of the heated floor area in some cities like Helsinki and Karlsruhe with more than 10%. In Budapest, this expansion is a bit lower, whereas for Milan and Warsaw, there's a reduction in the heated floor area in 2015. And also the specific average consumption between the scenarios varies. It's in some cases it's reduced around 20% and up to 48%. So the specific consumption in kilowatt hours per building square meter. If we have a look at the individual heat supply units, we know that currently individual heat supply is dominated by fossil fuel boilers. In our assumption, we've tried to actually we have assumed that the national results will also trickle down to on local level. From today's perspective, this is not correct, because we see large differences between the cities and within rural areas. But in the future scenario that we have considered, we see that there is a drastic increase in the share of individual heat supply by solar thermal and heat pumps, and which means that the differences between urban and rural areas will be much smaller in comparison to what we seen today. So if we have a look at the areas suitable for district heating, we can see that the build-up area varies widely between the cities and the scenarios, with Milan having the largest area suitable for district heating supply based on the assumptions and the scenarios that we have. In this case, the results are presented between minimum, average, and maximum. Since we have two variations. On the one hand, we have the different scenarios. On the other hand, we have also the different building connection rates. And we've seen that in Karlsruhe, for example, the share of total build-up area suitable for district heating by using this type of methodology is much smaller in comparison to the other cities, mostly due to the city building typology and population as well as building density. If we have a look at the district heating pipeline and the share of district heat supplied, we can see that the definition of suitable district heating regions leads to district heating reduction in the cities with high share of district heat in their current heat supply. This is mostly the case for the city of Helsinki and the city of Warsaw, where we actually see that if we apply this methodology and say, okay, let's just focus first and foremost on the regions with at least 25 gigawatt-hour per square kilometer density, then we can see that the share of district heat of the total heat supply reduces in almost all of the scenarios. Whereas on the other hand, we see high expansion potentials in Budapest and Milan, where especially for Milan, we can actually see that almost in each, due to the fact that the current district heating network as well as share of district heat is the smallest one, we see that there's some very high potential for the network expansion. Whereas for Warsaw and Helsinki, we actually see that the pipe length is reducing or could be reduced, and obviously this will impact the district heating share as well. If we have a look at one of the mostly used indicators to evaluate the economic feasibility, apart from the heat density, it's the linear heat density, which represents the heat supplied for 1 meter of the pipe. We can actually see that in almost all of the scenarios, the heat densities are above 1.5 megawatt hours per meter, which is seen from today's perspective as an economically feasible scenario. In Helsinki, in some of the scenarios, for example, we can observe the highest heat density of 5.9 megawatt hours per meter, which is a bit higher even than the current one. But of course, this is due to the fact that by predefining the district heating region, we are actually shrinking the district heating network only in specific areas, and this is mostly due to this predefined suitable district heating regions. If we look on the other hand at the heat generation capacities, there were also a few assumptions here. Apart from the fuel mix, we also wanted to calculate, or we have to calculate also the installed capacities, and we can see that obviously due to the reduced heat demand and heat densities and lower peak demand loads, there's less need to install district heating heat generation capacities, and also the price would probably increase. We have applied some assumptions and some fuel prices. Obviously, this is quite challenging actually to foresee some price development, as we all know, and but nevertheless, if based on what the assumptions that we have applied, we can see that the heat generation cost will increase, especially for the city, for example, of Warsaw, where they are currently using a lot of coal CHP power plants for the heat generation units, as well as for the city of Helsinki. And I see that there's a slight mistake here in the installed capacities. In Helsinki, something is missing, but okay, nevertheless, I think that the graph here, it's one generation capacity here is missing, but yeah. Anyhow, the key message will be that an increase in the heat generation costs can be expected due to the shift from coal-fired CHP power plants to renewable heat. On the one hand, obviously, if we just analyze the levelized cost of heat, on the other hand, the investment, the total investment, the absolute investment needs for the installed capacity will be lower due to the lower peak demand loads. And if we also have a look at the distribution the investment and the operation costs of the district heating network, we can actually see that an average price increase between 14% and 35% can be expected due to the reduced heat densities. Within the scenarios we have calculated, it was a bit challenging to show that we have calculated many different options, and the price range varies between 60 and 90 euros per megawatt hour, the working price for the district heating network, and this would be actually the influence on the district heating capex and opex, the influence of the reduced heat densities. So last but not least, we have the goal was obviously to calculate the total cost of heat supply, and we see that, for example, here we have the city of Milan. We have seen that up to 83% in some of the scenarios of the heat can be supplied by district heating in cost-effective manner, with the 1% refurbishment renovation scenario the cheapest one. Yeah, as said, in almost all of the scenarios, it's actually cheaper to invest in district heating in comparison to individual heat supply. Obviously, this refers to a certain specific level. If we go above this 83%, then this will change. If we have a look on another example, the city of Helsinki, as I've mentioned before, the predefined district heating regions of 25 gigawatt-hour per square kilometer reduce the current share of heat supply, and we see that by applying this methodology, we could supply in a cost-effective manner around 70% of the heat in 2050. If we further reduce this threshold of 25 gigawatt hours, there's still some potential for expansion of the district heating network, although it would not be expansion, it would be less shrinking of the network. But there's also a limit to this one, and from an economic, just from economic point of view, it might be reasonable for the city to reduce the district heating supply from the current 92% to around 80% probably in 2050, or maybe even a bit less than that. Since we don't have a lot of time, maybe these are only the two case studies that, although total costs that I wanted to present. Very few words about the discussions and conclusion. The improved building efficiency obviously affects the boundaries of the economic viability of district heating network in several ways. As we see, we can expect higher relative distribution costs, we can expect lower installed capacities, and we can also expect higher heat generation efficiencies. One of the major strengths of the district heating network is actually the ability to combine many heat sources and balance the impact of the high fuel prices. We applied obviously this generic fuel mix so that we can be able to evaluate the impacts between the scenarios, and even with this oversimplified generic fuel mix, we see that there is a potential for district heating network expansion in some of the cities, and that investment from our perspective, investment in building energy efficiency measures and connecting more buildings to district heating network in some cases can act as a safeguard against high future prices and reduce the risk of energy poverty. To conclude, we already mentioned that the heat densities can actually increase the relative price of heat distribution. Nevertheless, if we maximize the connection rate within the identified district heating regions, we will, in most of the scenarios, we will have a lower total cost of heat. And from our perspective, municipal heat planning as a strategic approach can ensure affordable heat supply by properly implementing and monitoring the efficiency first principle. Because I've put a lot of information, I know, in very short period of time, but it's actually quite challenging to consider all of the all of the data and all of the information and to model everything up until 2050. So in that sense, heat planning should be part of the urban planning, and this will be our recommendation, because otherwise we see that it's very difficult to see to which extent you should install a new heat generation capacity, to which extent you should expand the network, or in some cases reduce the network, so that you can provide an affordable heat to all of the citizens. And with that, I will conclude, and I think we have still 10 minutes. Sorry about that. I was actually hoping we'll have a bit more time for the discussion, but yeah, there are a lot of informations, and yeah, I had to compact everything in very few slides, so to speak. So I'm really looking forward for the question. I cannot see here, Jean-Sebastian, if you can.
Yes. So there are a few clarification to start. Maybe if you can go back to slide 24. Yes, about the levelized cost of heat. Does it include the carbon price? Because here you have for Warsaw a large share of coal, for example, and the cost is much lower in the current situation than in 2050.
Yes, but the price has increased. Also the CO2 price, although this I don't think it will have such a drastic impact. The prices are still quite low, and they use CHP power plants, coal-fired CHP power plants built many years ago. So the levelized cost of heat will probably increase if we apply the new ones. We have used CO2 costs from 2019, I think, or 2018. I have to check. So it's here, but not the current CO2 price, which is yeah, a bit higher. I think it's around 90 euros per ton at the moment, or around that value. But we haven't applied that here, so it's a bit lower. I think it was around 35 or 40, if I'm not wrong, which obviously cannot impact the prices. This is still a very low CO2 price cost to have a drastic impact on a coal-fired CHP power plant.
Yeah, no, that's clear. But as you say, yeah, that would probably change.
Here's some mistake, because for Helsinki, actually the installed capacities are higher, but I think I have missed some of the current heat generation units. But yeah, we will repair that mistake.
Yeah, no problem. The next question is about what you presented as total cost. So just to clarify, over what period is it calculated? Is it between now and 2050, meaning over 30 years?
Yes, and in this case, we are actually only we have selected 1 year, so this should be 2050. But obviously, there are some variations. Now the question will be with which tempo we can actually, which is also a very good point in the implementing on the energy efficiency principle, and why you need this municipal heat planning is because like if we have, for example, a certain period of time, I foreseen a certain period of time in which we will invest into the network itself, but the building refurbishment is not being completed at this step. Obviously, that will lead to an oversizing of the pipeline itself. So this is another challenge that we see, because if I connect customers today, I need to supply their needs today. I cannot say, okay, I have a lower capacity, I will supply your needs in 2035 or something like that. So this is a very good question, and that's why within the municipal heat planning activities, there's this reoccurring event where you have to actually prove and see, okay, what are the prices, what is the current development, etc., so that you can improve and you can make readjust the decision. So this the way I see the implementation of the energy efficiency first principle will be a reoccurring process. So this will not going to be, okay, I have calculated this and now I have 1 year. These are the data for, I think, 2015, what can be expected. So this, in my opinion, it's not going to work like that, and you need some reoccurring process in, I don't know, let's say 3 or 5 years, where you can reassess what actually has been implemented, so that you can really say that, yes, we are applying the energy efficiency first principle in our municipality, for example, or in our utility. Otherwise, it's quite challenging. Even if we add up all of the costs and say, okay, these are the added costs, to be honest, I don't know how much added value this has, because the tempo of investment can vary from one city to another. And the question is, when should I start expanding? Obviously, the best will be to invest in building efficiency measures and then expand the network. But as we know, this doesn't happen like that. So it's a continuous process of network expansion and building refurbishment. And if this is not being controlled, then which was not the case up until now, you might end up having an oversized network, or as we also see now, you have two infrastructures in parallel built, a gas network and district heating network, which should for sure be avoided. I hope I was.
That's clear. The next question would be about what you have shown in several graphs of the results, that the heating price, the district heating price would increase in most cases. And so the question would be, I guess, related to the general trade-off questions you mentioned at the beginning of your presentation. To what extent this higher heating price can be compensated by the lower heat demand due to the renovation of the building? So how do you see the, let's say, the optimization between?
Yes, so in order to fully optimize this, obviously, as I mentioned, this is one disadvantage, that we have applied a generic fuel mix, so that we are able to compare different costs. But in the reality, if, let's say, I work at the utility in Budapest, in the reality, the first thing that I will actually look at, it's the heat generation cost. So if I have a lower heat generation cost, that gives me a more freedom to expand the network. If I have a high heat generation cost, so so to speak, that then in that sense I am already bounded to this heat generation cost, and if I expand drastically the network, and at a certain point the customers are not willing to pay for it, then and they start disconnecting, this will have an exponential impact on the cost. So if the customers start disconnecting due to some high heat generation costs, and due to the fact that I have to shift now from coal to, I don't know, let's say geothermal heat, and although the price probably will not be that high, but still, I mean, it's a mix from different factors, different impact factors. So it's not that easy to have a look on a different cities with different typologies within Europe and to come up with one conclusion. One interesting indicator is, of course, the linear heat density. This is you can apply it everywhere, so to speak. But there are also utilities, like for example in Germany, they say that, well, this is too low. Anyhow, we don't want to go below 3 megawatt hours per meter. This is from today's perspective, of course, 3 megawatt hours per meter, but this will change in the future. And as I said, if we have a cheap heat source, this indicator can go even up to 1 megawatt hour per meter. But if you have a bit higher costs than you have today, then it will be difficult. So this is a question that I know many utilities are already dealing with, and how to actually avoid this issue in the future when you shift from very cheap to a bit higher heat generation costs. How can you keep the customers, so to speak, connected? Because if they start disconnecting, you probably see some scenarios like in many Eastern European cities at the beginning of 1990s, where many people are not able to afford the increased prices of district heating, and we know that the share of district heating, although still much higher than in Western Europe, we know that many district heating networks even cease to exist due to this fact.
Thanks, Eftim. And there is one last question that is related to the assumption you made on the renovation refurbishment cost. To know, and that's from Damir Stanicic, did you take does this renovation refurbishment cost include only the cost for the energy part, let's say, of the refurbishment, or is it including also other costs like the regular maintenance of the building, the structural renovation, let's say?
As far as I know, from the Ingrid model, it's both are included. Yes, so that's why we actually, if we want to calculate the total cost of heat supply, we need to consider all these three factors, right, within all the scenarios. On the one hand, what would be the grid heat supply? On the other hand, what is the individual heat supply, and as well as the building refurbishment cost, annualized, obviously, throughout the years, and presented in euros per megawatt hour or euro cent per kilowatt hour, so that you are able to compare this cost with the other costs as well.
But it also
so
means that
are included.
Mm-hmm. So it also means that part of this renovation cost would happen anyway, right?
Yes.
Because the buildings will need at least part of the.
Yes.
Okay. No, that's all clear. I see that we have reached the time. So I thank you very much, Eftim. I think that was very inspiring to see these results. And anyway, we encourage also the participants to contact us if you have further questions or you want to get further details. And in the coming months, the report about these case studies will be published on the website, probably in the month of May, I think. So after the end of the webinar series, you would get the full report about these case studies. And there are also papers about these case studies that are currently submitted for special issues in journals about the energy efficiency first principle. So with that, I thank all the participants for attending. Thanks again, Eftim, and thanks, Margot, for organizing this. And I hope to see you in 2 weeks for the next webinar that will be presented by Tim Mendel from Fraunhofer ISI about energy efficiency first in commercial areas. Have a nice afternoon. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.